So, hello again to the Advanced Algorithm course. Today we will continue in Chapter 3 Problem Solving Paradigms, and we arrived at the subsection 3, which is about greedy greedy paradigms. So, we saw together complete search, we saw divide and conquer. Now we are going to see the greedy paradigms, and next we will see the most difficult part, which is dynamic programming. We begin the greedy paradigm and we define what is the meaning of greedy. Greedy is having an as per the dictionary, it is having an excessive desire or appetite for food. So you want to eat food all just at once. You don't want to wait and eat it by order. Having or showing an intense and selfish desire for wealth or power. So this is greedy, tamma. So, what is a greedy algorithm? An algorithm is said to be greedy if it makes the locally optimal choices at each step with the hope of eventually reaching the global optimal solution. You have to know that in some cases, greedy works, the solution is short and runs efficiently. But, however, for many others, it does not. A problem, in order to be addressed in a greedy solution, must exhibit two properties. The first is to have an optimal substructure. So you can have an optimal solution for the problem, for the sub-problem. So you can stop the problem at the middle, at some iteration, at some value, at some level, and say, I want to solve this part until now. Can I find a solution? If you can obtain an optimal substructure for your problem and you can provide a solution for this sub-problem, this is a property, this is a sign that it may be solved using greedy paradigm. The second property is the following, is to have a greedy property. What is the greedy property? It is difficult to prove in time critical contest environment, but you have to have the sense. The sense is if we make a choice that seems like the best at the moment and proceed to solve the remaining sub problem, we reach the optimal solution. What does this property differ of the previous one? The previous say that for a sub-problem we can find a solution which is optimal until now. The second property says if we continue we reach the optimal global solution. So you will never have to reconsider our previous choices. So you don't have to move backward in order to make some changes. So this is only move forward solution. If you don't have these properties, you cannot find a greedy paradigm to solve your problem. Let's take some examples. We begin by the coin change, the greedy version. So the coin change problem is a difficult problem. We have a greedy version that works for some of the cases, but the most difficult one will be we will see it together in the dynamic programming. Let's read the problem description. Given a target amount V cents, so you have coins, you want to reach your target, you want to pay, let's say, the value V of cents, and a list of denominations of n coins. So you have a list of n coins, and the coin value I for I is between 0 and n minus 1. So you have n choices, and for each choice you have the coin value. Okay? What is the minimum? What is the problem? The question here. What is the minimum number of coins that we have to use to represent an amount V? Okay, so let's say I have this example. Assume an unlimited supply. Let's say I have this example, n equal 4, and you have 4 different values. And the coin values, the 4 different coin values are 25 cents, 10 cents, 5 cents, and 1 cent. And here you can see the 1 cent. So using the 1 cent and the property that you have unlimited supply, the problem is not to find whether I can pay this amount, this V amount or not, because suppose your V is 17, you have the first solution, 17 cents, each 17 coin, each coin of value 1 cent. So everything will have a solution, but the question is, what is the minimum number of coins that we must use? We cannot use less in order to represent V. So this is a problem. And for example, for n equal 4 and for V equal 42 cents, the greedy solution will say, okay, I have to use the minimum number of coins, so let's use the coins with the maximum values, okay, first. And then if the amount left to be satisfied is less this maximum value, I take the next maximum value, and so on. So let's consider I want to represent the value 42. I will take the maximum coin, which is 25, and I have the remainder 17. I take 17 in order to satisfy it. I look again at my set of coins, and I find again that I can have 25. However, if I use again 25, it's more than 17, so this is not possible. If the value V is big enough, maybe I take two times 25, there is no problem. But here I continue, I will not take 25, I take the next maximum, which is 10, and 17 minus 10, I will have 7 cents remaining to represent. So you see, we have here sub problems. Now my problem is to satisfy the value V, which is now 7, and using the minimum number of coins. And again, I cannot use 10, so I can use the coin of value 5, and I will still have 2 to satisfy, and then I can only use the 1 cent value. I use it and I will have a remainder 1, and again I will use the 1 cent value, and thus I have used the coins 25, 10, 5, 1 and 1. And so I have used 5 coins, and this is an optimal solution. There is no better solution. There is no other solution that uses less coins in order to satisfy the value amount 42. So here we have two ingredients, and it is obvious. The first one we talked about, we have the optimal substructure, the optimal solution to subproblem contained within the solution. So the 17 cents is a subproblem of the problem of 42 cents. And the optimal solution for this subproblem, which is 10 plus 5 plus 1 plus 1, is a part of the global solution, because we add only the 25 and we have the solution. So we have the optimal substructure and the greedy property. So using any other strategies will not lead to an optimal solution, and we move only forward. However, this does not work for all the lists. Suppose I have the list 431. Okay, let's take another example. I have the list, instead of coin values 25, 10, 5, 1, I have the list 431, and the value I want to satisfy is 6. If I proceed using this greedy paradigm, I will choose 4 first, and I will have a remainder of 2, and in order to satisfy 2, I don't have the value 2, the value 3 cannot work, so I use 2 cents each of 2 coins each of one value 1 cent, and this gives me 3 coins. However, we all know that if we use the coin 3 two times, so I will have used only 2 coins, and this is the optimal solution. So that's why we said this is the greedy version, and the general version we will see it together in the last section of the paradigms in the dynamic programming. So let's take the first example of such problems that can be solved using greedy paradigms. The first one is about load balancing, and it is the UVA 410, which is named station balance. And we read the International Station contains many centrifuges which in its lab each centrifuge will have some number C of chambers, each of which can contain 0, 1 or 2 specimen. So the centrifuge it turns to in order to make a resemblance that there is no gravity, and each centrifuge has many chambers, has C chambers, and in each chamber we can put 0 specimen, 1 specimen, or 2 specimen. A specimen can be an animal, vegetal, mineral, anything that you want to study. You are to write a program which assigns all the specimens to the chambers. Okay, we will distribute the specimens to the chambers such that no chamber contain more than 2 specimens, and the following expression of imbalance is minimized. So you have C chambers, you want them to be balanced inside the centrifuges of the International Space Station. In order to be balanced, you have to minimize the imbalance. What is the formula of the imbalance? It is the summation of the difference of the cumulative mass in each chamber minus the average mass that should be in each chamber. So you have to minimize this formula. Let's read again this problem written nicely here. So given C chambers where C is between 1 and 5, which can store 0, 1 or 2 specimens, and S which is less than 2C, S is between 1 and 2C specimen. Okay, this is the number of specimen, and a list M of the masses of the S specimen. Okay, we have S specimen and we give the mass of each one. And the question is to determine which chamber should store each specimen in order to minimize the imbalance. So we will have to determine the distribution of the specimen over the chambers. And we have the average, which is the sum of the masses divided by the number of the chambers. And this is the total mass, the average of total mass in each of the chambers. And the imbalance, which we saw in the previous slide, is the sum over I from I equal 1 to the number of chambers of the difference in absolute value between xi minus a, and here xi is the total mass in chamber I. And this is the imbalance, and we want the minimum imbalance. Okay, how to distribute? Let's see an example illustrated on the right. Here we have 3 containers, C1, C2 and C3, and we have C equal 3, so, and S equal 4, I have 4 specimen of respective masses 5, 1, 2 and 7. What is the average? It is the sum of the masses divided by C. It is equal to 5 plus 1 plus 2 plus 7 divided by 3, which gives me 15 by 3 equal 5. Okay, let's consider I distributed without taking into account this imbalance formula. Let's calculate the imbalance formula for a random distribution. Suppose I put the 5 and 7 inside the first chamber, I put the 2 inside the second chamber, and I put the specimen of mass 1 inside the third chamber. So I have to calculate the imbalance to see whether this is a good imbalance or not. The imbalance is equal to 12 minus 5 in absolute value plus 2 minus 5 plus 1 minus 5, all in absolute value. So 7 plus 3 plus 4 equal 14. Is this the optimal distribution? As you can see, this is far from being the optimal distribution, because every cumulative mass in every chamber is far from being near the average value, which is 5. Okay, so how to proceed? Do I have really to do the complete search to explore every possible combination of solutions? Is this even possible, or do I have another way? So let's make an observation, and we start by the first observation, observation number 1. And we remark that if there exists an empty chamber, we have to make the choice to move one specimen from a chamber with two specimens to the empty chamber. So what does this say? We don't want to keep empty chambers. Okay, if we can fill all the chambers, this is better. So if it doesn't improve the solution, it is guaranteed not to make it worse. It will never make it worse if we move one specimen from a chamber containing two to a chamber with zero specimens and we put it here. Because suppose it was near the average, the cumulative sum. If we move it and put it in an empty chamber, the difference here will be reduced by the amount that the difference was increased. So this will not worsen the case, and if we are lucky, it will improve the case. So this is observation number one. We don't want to leave empty chamber if possible. If this is not possible, we don't have a choice. So suppose the number of specimens is less the number of if the number of specimens is less than the number of chambers, so obviously there will be empty chambers because we distribute the specimens. However, we distribute the specimens, there will still remain empty chambers. So we don't really have choices to make. So this is not the case. The problem is not here. The observation number two is the following. If we have more specimens than chambers, if S is greater strictly than C, then S minus C specimens, okay, we can distribute the first C specimens over the C chambers. This is what we said in observation one. But the rest, the S minus C specimens, must be paired with a chamber already containing another specimen. What does this say? This is exactly the pigeonhole principle which we are going to see in the next slide. What is the pigeonhole principle? The pigeonhole principle in mathematics is the following. If you have n items that are put into m containers where n is greater than m, then this says that at least one container must contain more than one item. Look at the right, and this is a pigeon in holes. We have pigeons here. There are n equal 10 pigeons, and there are only m equal 9 holes. And as you can see, that there is a hole that must receive two pigeons in order to satisfy the arrangement. Okay? The pigeonhole principle says that at least one hole has more than one pigeon. And this principle was first introduced in 1624 by Jean Le Rochon and was restudied in 1834 and retreated by Dirichlet. And the problem was known by the Schubfach-Prinzip, which is nothing else but the drawer principle, or also referred to by the shelf principle. Who are these two scientists? Jean Le Rochon was a French Jesuit priest, astronomer, and mathematician, known for inventing the pigeonhole principle and naming the thermometer. So this was a very strong mathematician. Dirichlet was a German mathematician who made deep contributions to the number theory and to the theory of Fourier series and other topics in mathematical analysis. He is credited with being one of the first mathematicians to give the modern formal definition of a function. So this was a very important scientist. Back to our problem, and now we know that we are dealing with the pigeonhole principle. What are the key insights? One key insight is the solution can be simplified with sorting. If S is less than 2 times C, the number of chambers, so we cannot put exactly 2 specimens in each chamber. It is easy to add what we want, to add the difference of 2C minus S dummy specimens with which masses, with the masses of 0. Okay, so we sort and we add dummy specimens. Here you go. You have 7, 5, 2, 1, the first 4 specimens, and you need, in order to fill in each chamber 2 specimens, you need 2 more, so you add the dummy specimens, which are of masses 0 and 0. And the greedy strategy is very simple, you already know it now. You have to pair the specimens from the two extremities and put them in chambers. So you take uh, first extremity, this specimen, which is a dummy, is 0, with this specimen, which is the maximum, 7. 0 plus 7, I put it in the chamber number 1. Next, I go to the extremity, 0 plus 5, I put it in chamber 2, and I still have only the specimen 1 plus 2, I put them in the specimen 3, and this is guaranteed, this is obvious. If I put the maximum and the minimum always, and I move from the two extremities towards the middle, this is guaranteed that you have the optimal imbalance, that you will have the minimal imbalance, and there is no other imbalance that can be minimum. Another kind of problems that can be solved using greedy paradigm is the interval covering. Let's study this problem taking an example, the UVA 10382, which is watering the grass, and let's read together. And sprinklers are installed in a horizontal strip of grass L meters long and W meters wide. Each sprinkler is installed at the horizontal center line of the strip. For each sprinkler, we are given its position as a distance from the left end of the center. It means from here, okay, as a distance. For example, for this circle, you take its position as a distance from the left end of the center line and its radius of operation. So the stringer has a radius of operation and a diameter of operation. What is the minimum number of sprinkler to turn on in order to water the entire strip? So you have a strip of grass. Okay, this is a strip of grass, and you have sprinklers that will provide water in order to water the grass. And you have n sprinkler in a strip of grass. You have the length of the strip and the width of the strip, and you have the number n, which is less than 10,000. This is a pretty much big number. And each sprinkler is centered vertically in the strip. Okay, so it is in the middle vertically, it is centered, and we have its radius, the radius of its operation, and its position. Okay, and the position is the distance from the left end of the center line. What is the question here? The question is, what is the minimum number of sprinklers that should be turned on? Okay, we can turn them on all, but this is not the minimum number, of course. We want the minimum number that should be turned on in order to water the entire strip of grass. Example, in here you have the example of the problem given inside the problem. The answer is 6. How is 6? If we number the circles of operations from the left to the right, we will have A, B, C inside B, D, E, F, G, and H. We can know that we can easily not turn on the operation sprinkler C and G, and we can still water all the strip grass because the area covered by the C and G are also covered by other sprinklers. Okay, so do we have the choice of a complete search of a brute force strategy? Can we imagine trying all the possible subsets of sprinklers to be turned on? What if I turn on A and B and turn off the rest, etc.? What is the number of those possible cases? 2 to the power 10,000. And this is infeasible, of course, because already when you are 2 to the power 30, this is 1 giga operation. This is huge. To the power 30, not 2 to the power 32. 2 to the power 32 is even worse. And imagine 2 to the power 2 to 10,000. So this is not an option. And here we have to think of another way. The other way is that this is also a very known kind of problem. This is an interval covering problem. We will see it with a simple geometric twist. Let's see together what is interval cover problem. This is a problem of the sort of set cover problem. And the set cover problem is a classical question in combinatorics, computer science, operation research, and complexity theory. And this is one of the CARPS 21 NP complete problems. And especially this set cover problem that we will discuss now, its study has led to as per the Wikipedia site, its study has led to the development of fundamental techniques for the entire field of approximation algorithms. So you have approximation algorithms. There are algorithms, there exist algorithms that will give you an approximate solution that is very good enough to consider, because the real solution is very complex to find. So, what does the set cover problem state? Given a universe from 1 to n and a collection S of m sets whose union equals the universe. So, you have the universe, an interval from 1 to n, or a set 1 to n, okay, n elements, and you have a collection S of m sets, okay, whose union is equal to the universe. What do we want? We want to identify the smallest sub-collection of S whose union is also equal to the universe. So no need to the other subsets, to the other elements in S. Let's take an example. Given the universe U, which is equal to 1, 2, 3, 4, 5, and the collection S, which contains four sets, set 1 to 3, set 2 4, set 3 4, and set 5 4. And what is the smallest subcollection of S whose union is equal to the universe? Obviously, you can take 1 to 3 and 4 5, and the union of 1 to 3 and 4 5 gives me U. So this is enough. So this is the smallest number of sets I can take from S and to cover the universe U. This is the set cover problem, and it is our problem here. In the interval covering, however, we have to make a small simple geometric twist that we must take into account. What is this twist? It is the following. Consider this is the radius and this is the strip, and you'd all remember that the strip has a width, okay? The sprinkle can only cover entirely the entire part of the strip going from this line, I will draw it in red, this line to this line. So the blue line here, the interval here. What is the interval here? It is not x minus r plus r. It is x minus gx, x plus gx. And here gx is given by the Pythagorean formula. You have the height, which is width over 2. You have the radius, And you have the Pythagorean formula, which gives me R2 equal W over 2 to the power 2 plus dx to the power 2. So I obtain this formula. How do I calculate dx? Dx is square root of R to the power 2 minus W over 2 to the power 2. And this is the area that the sprinkle can completely cover and can completely water, and the others are not completely watered over here, for example, over up and down on the strip. So those are our intervals, x minus dx, x plus dx. And now the greedy solution comes and says, simply sort the intervals by the increasing left endpoint. Okay, so I begin with the smallest left endpoint, and I continue increasingly. And for two equal left endpoints, sort them by the decreasing order of the right endpoint. So if you have two circles that if you have two intervals that begin from the same left endpoint, one is bigger than the other, then the bigger must come first. So you sort the intervals. Once you have the centers, you have the radiuses, so you have the intervals, and you sort them like this, and then take the interval that covers as far right as possible. Okay, and you have to choose an uninterrupted coverage. You cannot choose the circle A, for example, the interval covered by the circle A, and directly the interval covered by the circle D, because there will be an interrupted covering. Okay, so you have to choose the circles that the intervals that cover as far right as possible, and that was not covered before, but without interrupting. Without, you have to take an uninterrupted coverage, so you can take overlapping circle if necessary, and you have to ignore intervals that were already covered by previously chosen intervals. Remember, this is a greedy solution. It proceeds forward, so we don't go backward. We never reconsider our choice, so we ignore the already covered solution. Let's take this example in order to understand how it worked. We sorted the circles. We sorted, excuse me again, we sorted the intervals, and we have the sorting A, B, C. B comes before C, of course, because we consider the increasing left endpoint, the left endpoint first. So B have the left endpoint before C, and then D, E, F, G, and H, just like the letters go. And then we take A, we have to take A, we have to consider A, because the area covered by A is not covered by another interval. And then we have to take B, we are obliged to take B, because it covers the far possible area, the as far right as possible. So B is big enough, it comes before C, we take it. And then we have to ignore C, because the interval covered by C is already covered by B. And then we take D, because if we will ignore D and we take E only, we take A, B, E, there will be areas here that are neither covered by B, neither by E. So B intersect E is the empty set, so we have to take D in order to cover these uncovered areas. And then we take E, F, we ignore G. Why do we ignore G? Because and take S, because G does not go as far as possible, and because if we take H, it goes as far as possible, more than G, and F intersect with H is not the empty set, so G will be already covered by H. And this will lead to the minimum number of 6 sprinkles. Here is the code. So let's consider the solution of this problem, of the grass watering problem UVA 10382, also provided by the Competitive Programming 3 book. We begin by including bits/std C++.h using namespace standard, and remember we will be going to deal with floating points, so there is no equal comparison because floating point as imprecise. Remember the geometry lesson, so we define the epsilon small value to compare floating points differences, etc. And we have here a structure, we call it SP. It has a center. We don't need the ordinate of the center. They don't give it to us because they are centered in the middle of the strip vertically. We have the x and the radius, and we define the left bound and the right bound of the intervals, so we will fill them later. We will read the x and r's, and we will deduce the x underscore L and x underscore R, which are x plus and minus and plus delta x. And here, how many sprinkler we have? They said we may have 10,000. So I always, when I have to define arrays, I define it a little bit bigger so that I don't overflow. I don't go out of bound of the array. And here I am defining the comparison function that will be used in sorting. We said we will be sorting the array of sprinklers according to what? According to the left bound and to the right bound of the intervals of these sprinkles. So I will be calling this comp here. Let me show you. I will be calling here. Okay, I will be calling it, giving the address of the array sprinkle and the end address, so sprinkler plus n. This is the last address after the last element. And how do they sort? They sort with respect to comp. Comp is a Boolean function that takes two sprinklers and return true if A should come before B and false if A should come after B. And so for not the same left endpoint, we will return the left endpoint that comes first. So we will return true if a dot x underscore l is less than b dot x underscore l. And if the difference in absolute value is less than epsilon, so they have the same left endpoint, we will compare the right endpoint, but this time the far right endpoint will have to come first. So return a dot x underscore r greater strictly than b dot x underscore r. This here strictly or no is not a difference, is not going to change because first we have the floating point, and second this is not going to change in the sorting algorithm anything. Okay, so here we go. This is the main function. We will loop and keep reading N, L, and W. And then, what shall we do? We will, if we will read N times, we will read the sprinkles. So we will store them in the X and R of every sprinkler of I. And this is how many times for I equals 0 to N. And then we will proceed by calculating the left endpoint and right endpoint for each sprinkler. So we will fill those two fields, x underscore L and x underscore R. And what do we say if the sprinkler radius is less strictly than the width of the strip, so it cannot water the strip even for one point. It cannot water all the width of the strip. So I go directly to the else, and here in the else the left and right endpoint are the same and they are equal to the solo point, which is x. So this is to make this unselected. It will not be selected. This is an interval reduced to one point. And if it can water, I will do what we already saw in the slide. I will calculate delta x, which is the square root of the radius to the power 2 minus w over 2 to the power 2. And I will store the x L, which is x minus delta x, and x underscore r, which is x plus delta x. Here I have filled my array of sprinkler for the n sprinklers. What shall I do next? I sort using the comparison function I have defined. Okay. Now I have the intervals all sort nice and smooth, and I begin my search. How do I begin my search? I define a variable called possible, and maybe the sprinkles they give me, they don't cover all the area. So in this case, anytime I will see discontinuity, I see uncovered area, I jump from one interval to another interval directly coming after it with no intersection. So directly I will put possible to be equal to false. Okay, here after this we will reach it. If sprinkler dot of I dot xl is less than covered, I continue. If the left end point of the current sprinkler I am studying now, which should be they are sorted in increasing order. So if this left end point is not inside the area covered, so there is discontinuity, directly I put possible false, and I go out of the game. Okay, I will print -1. And also I will print -1 in another case if I finished the loop, I finished all the sprinkles, but I didn't cover the full length of the strip. Okay, so I will go inside this loop for every sprinkler. Okay, and while it's always possible, while we have always a hope to find a solution, I plus plus. Okay, this is early pruning. If I already covered the length of the strip, I will break, finish, I reach my solution. And else, if I have the right endpoint already inside the covered area, because I initialize the covered first before I begin the cover. I didn't cover any area. Okay, and one by one interval by one interval, the covered area will take the right endpoint of each selected interval. Okay, the most right endpoint it will be. So if I have the current sprinkler under study, the right endpoint already less than the covered area, so this full interval is inside the covered area. I don't need it, it is already covered. Okay, else I go into the second if the sprinkler of I dot left endpoint is inside the covered area. Okay, I will consider it, but I have to compare it with the following sprinklers, because maybe there exists another sprinkler that comes after and it goes far more. Okay, so I take the double max R, I initialize it to a negative value, and I go to find the maximum radius, to find the maximum coverage from j equal I, which is the current, to the end of the sprinklers. And while the left bound is inside the coverage area. Okay, so I take, because I don't want discontinuity, while the left bounds of the sprinklers of J is inside the area, I consider them, and I will only keep the interval of number j whose right endpoint is the farthest from the for the strip. Okay, and once I find it, I take it, I count it in the plus plus answer, and the covered area now receive its its right bound. Okay, and this is very easy. Else and if I don't find a equal solution, I say, and if I find a solution, I print answer. One final classical greedy solution to classical problem is to sort the input first, and we will take the example of the UVA 11292, which is the dragon of Loowater, and here you have a beautiful story about a kingdom where there is a king and knights and dragons, and the shortened problem description is the following. So you have n dragon heads, you have a dragon with n heads, and you have handsome knights that want each to cut a dragon head. And you have that m is bigger than n, m and n are between 1 and 20,000, and each dragon head has a diameter d, and each knight has a height h, and the knight cannot chop the dragon head unless his height is bigger than the diameter of the head of the dragon. Okay, so every knight can cut the head that is whose diameter is less than his height or equal. Okay, and we have also another condition that every knight can cut only one head. Okay, at most. And given the list of n diameters and the list of m heights, the question is the following. Is it possible to chop off all the dragon heads? And if yes, what is the minimum total height of the knights used to chop off the dragon heads? Because here the king must pay the knights, and he must pay by the total of their heights, so by the centimeters of their heights. So he doesn't want to pay a lot. So what is the minimum total height of the knights used to chop the dragon heads? And here this is a classical bipartite machine problem, and in which there is a condition. You have to pair a knight with a dragon head, but you have to pair in a maximal fashion. Okay, and the greedy paradigm comes. You say the dragon head should be chopped by a knight with the shortest height that is at least as tall as the diameter of the dragon's head, because you don't want to use a very tall knight in order to cut a very thin head. You have to choose the shortest knight that is capable of chopping the head. So the idea here comes, sort both lists, and this is the order of n log of n plus m log of m complexity, and then you use another algorithm of the order of minimum n mn, so you only loop once inside both arrays, and you pair the minimum with the minimum, the minimum head with the possible minimum knight, if any. And whenever you end, either you print that Loowater is doomed, there is no possible solution, I cannot find enough knights, or you print the cumulative gold you was accumulating inside the variable gold. So let's check this small and beautiful code here. We have the type vector. We define it, type def vector of int vi, so that it will be short. We have the vector of integers, inside which we have in fact two vectors. We have one for the diameters and one for the height, one of n elements and one of m elements. And let's write on the slide here. We have N and M, and we scan them, and we say while they are not null values, I will define the vectors and I will fill those vectors. So I will go from g equals 0 to n, and I will scan f and inside my vector, and then inside my height vector, and then simply I will sort these two vectors in full range, and I have now them sorted. And then while d is less than n, okay, I didn't explore all the heads, I didn't shop all the dragon heads, and while I'll still have knights inside my set, I still have available knights. Okay, this is an inner while loop, but don't be afraid. They are not going to do exponential complexity because they are advancing the same indexes. Okay, so while k is less than m, always I still have possible knights to chop any heads, and while diameter, okay, is greater than the height, it is not possible to use this knight in order to chop this head, so I have to check the next knight. Remember, they are sorted. So if I find the negation of this condition, it means if I reach k equal m, this is I didn't find any knight. Else I break, of course. Else that this condition was false. This condition was false. That means that I found a k for which the diameter is not greater strictly. The diameter is less or equal. So this k, this knight, can kill this head. So I increment the gold value with the height of this k, and of course I already used this k, so I increment it here, and I already killed the dragon head, so I increment it here, and I will go to the next iteration of the outer while. Okay, and if I finish the loop with d equal n, it means that I killed all the dragon, and else it means that Loowater is doomed, and this is it. This is the end of our solution. We will terminate this greedy section by some small remark. You will understand them directly because you encountered them in those three problems. We have seen together the remarks are about greedy algorithm in programming contests, especially. We have seen together three classical problems that are solvable with greedy algorithms. So forget the advice we gave you in the beginning of this chapter about don't memorize the solutions. You have to learn how to have the solutions. It does not apply here because in greedy problems you have to memorize the solutions. You have to say this is a bipartite, this is an interval set, this is a covering, etc. And you have to memorize how do we solve them. The important strategy is always to sort the input data to elucidate the hidden greedy strategy. So you will think first, I sort the data, maybe I will have the greedy solution. And second, two other classical examples, we will see them later in this course, and we already saw them in the graphic theory, which is the Kruskal and Prim's algorithms for the minimum spanning tree. Okay, those are greedy algorithms, and also Dijkstra for the single source shortest path, which is a greedy algorithm, and we will see them later in this course, also in the chapter of graphs. The greedy is risky, you have to know, because okay, you will not have a time limit because this is a very fast solution, but maybe you will have a wrong answer because maybe your solution will not give you an optimal solution. So you have to be prepared. the proof is time consuming. You cannot prove before you use it. The rule of thumb here is the following. If your input is small enough for accomplishing a complete search or dynamic programming, then just use those two paradigms, either one. Of course, first you choose complete search. If your complexity is big, go to the dynamic programming. Else, if you don't have another choice, you have to see the greedy option. However, the problem setters set the input bounds ambiguous. So sometimes it is ambiguous how you have to calculate the input size and the complexity of your problem. So this is even more challenging. And the contestants cannot quickly determine the required algorithm, so you lose some time. And luckily enough, there is no much problems that are novel that need greedy solutions. So the greedy problems, the number of the greedy problems is low. So luckily enough, if there is a greedy problem, hopefully it will be one of the greedy problems you encountered during your preparation for the contest. So this was about the greedy section. Next, we will see the dynamic programming section next week. And we will see that the key skills that you have to develop in order to master the dynamic programming are the abilities to determine the problem states and to determine the relationships or transitions between the current problems and their sub-problems. And this is another definition, another strategy, another different paradigm that we will see.